Hello everyone, welcome to the backend of a global visual effects pipeline. The motivation from this talk came from last year when I was at PyCon Toronto, and no one had any idea we used Python. And I had no idea as well before I entered the industry. So I hope that by the end of this presentation you guys can have a better overview of how Python is widely used to produce beautiful images. I'm a lead core developer at Method Studios in Vancouver. Method Studios is an award-winning international visual effects group with facilities in LA, Vancouver, New York, Chicago, Sydney, and Melbourne. We serve high-end feature film, commercial, television, games, and motion graphics clients in the global marketplace, and we are hiring. If you know Python and what I talk about here interests you, let me know. I'll start by giving an introduction on VFX, followed by the backend necessary for the VFX house to do work, how we keep this backend in place, and with a conclusion in the end. So before we start, what is visual effects? This quote from Wikipedia, as usual. Visual effects involves the integration of live action footage and generated imagery to create environments which look realistic but would be dangerous, expensive, impractical, or impossible to capture on film. Visual effects is not limited to just feature film. In fact, almost every form of visual media today utilizes some level of visual effects. Classics such as Terminator, Star Wars, and The Matrix showed the audience visuals they could only dream of, and we can see how the commercials in particular have been getting a lot of visual effects lately. With the advancements in technology, better quality visuals are created each day and are now also part of the TV and the commercial world. We will cover the work, the process, the departments, and the applications behind VFX. So every time we are faced with new challenges that are only limited by someone's imagination, usually the director, the challenges of doing a CG-generated creature like Oksha are very different from the challenges of doing a superhero movie like Superman. We never receive the same show twice. Every show is very unique in its challenges. And I think it's fair to say that today we can achieve basically anything with visual effects as far as image goes. So breaking it down, when we receive the work from the client, we divide it into components to better manage it. There is the show, which is the project, be it a TV show, a commercial, or a film. Those shows, those project size, they can range from weeks to years. And they can have teams as large as like thousands of people. You guys probably saw the credit list at the end of the movies. That's only a fraction of who actually works on those movies. So the sequence is how we sort relatively similar chapters of the project. It's a smaller chunk of the overall story. The shots is usually a single movement of the camera. So sequence have a lot of shots inside it. And the task refers to the type of the work an artist may be performing the shot, like doing a 3D model, for example. In this example, you can see like what the file path would look like for a model task in the shot ABC 1000 of the show VFX PyCon. In VFX studios, they receive work by bidding on shots for a show. It is not unusual for different VFX studios to be working in the same movie, the same sequence, but in different shots. So the process of VFX is a common one. We take some form of input from the clients, such as role plays, concept work, or an idea, and turn it into a product for them. Our final products are usually images. We work with our clients during the entire process, using their feedback to shape the final image. There's a lot of back and forth and iterations between us and the clients. Some projects, when they're close to delivery, it goes often as daily reviews of our work. Internally, you break down the work into smaller chunks executed by different departments. Each department follows the same process of transforming an input into a product. For VFX, the product of one department will be used as input for the next department. This will continue until we have the final product. Here we can see how the Roto department has outlined the couple, and the paint department has painted out non-relevant parts of the image. There are many departments involved in creating the final product. This is a summary of the departments that we have at Method Studios. Each department has its own teams, leadership, tasks, and goals. And all of those departments will be working at the same time on a given shot. And the work flows from one department to another. The lines there, they are a simplification because in real life it would be more like this, where every department is connected to almost every other department and the work flows around it. Python is the common ground between all departments, tools, and libraries. It is the standard language of visual effects. Every application ships with a Python interpreter, which allows us to interact with the application at the same time as we interact with our own libraries. At this time, Python 2 is still the standard in the industry. However, there are plans to change that to Python 3 by 2019. As we are dealing with two-dimensional images and three-dimensional objects, we use different applications to do work. Maya is a 3D application that is used for computer-generated objects. This will then be converted to 2D images and integrated into the shot. Houdini is a 3D application that specializes in particle simulations. It is very similar to some form of visual programming, where you have nodes with inputs and outputs, and those nodes do some sort of transformation, and then you just connect all of them together. Nuke is a 2D application that allows the blending of the images. It is like a Photoshop for image sequences with a wider range of tools specifically to VFX. The layout department, as an example, we use Maya to position different objects into a scene being a 3D space where the environment will be rebuilt and reconstructed to real-world measurements, similar to how an architect may model its building. The challenge is altering the settings on those individual objects when there are thousands of them into a scene, and we use Python to address this. One of our libraries will query the database to load from, in the scene and update object information such as version, level of detail, file type, and status. When you're iterating your work, you usually load objects with very low level of detail, otherwise it wouldn't fit in a computer RAM, and we have like 100 gigs of RAM in each machine. FX uses millions of particles to generate fluid simulations like water, smoke, and fire, or ridge dynamics like impacts, glass shattering, and debris. Those particles are manipulated through Python scripts, that can involve up to 250,000 functions, all controlling the effects for one shot. Individually modifying all these nodes would be impossible, so instead we group them together and expose more useful controls to the user. For example, a group of nodes that generates this wave might expose controls like speed, size, movement, and color to the user. This group can then be stored and used by future artists when they need to create a wave. The node group that we just mentioned would be called an OTL in Houdini and be stored into an OTL database, as we can see there. Python libraries will also use the Houdini API to import objects such as cameras, 3D models, and animations into the work file of the artist. Once the work is finished, outputs are generated for other departments to consume. Think of the wave as an image sequence that a 2D department can use to blend into the shot. Compositing is the final step of the overall process. They shape, blend, and alter image sequences into the masterpiece we as the audience see in the cinemas. Nuke allows us to create custom callbacks in Python for different parts of the work that is done. In this example, we are creating a callback to make sure a directory exists before rendering it to the disk. A big number of formats are used by different tools and departments. Conversions need to happen automatically between those formats so that the work can flow easily between departments and artists. A mix of Python library and command line tools, which we usually call from Python, are used to do this job. Here you can see FFmpeg creating a video from an image sequence, EXRs being exported to JPEG, and Maya exporting an ABC cache. These ends are very brief introduction to VFX, just so you guys have an idea of what's going on. We saw how we can use Python in different tools and departments and how we can glue them together and do transformations, but we didn't talk about C++. C++ is used mostly in the development of the VFX tools themselves or in plugins for those tools. Certain departments can have C++ developers. For example, the FX department might have someone working a new fluid simulation algorithm for Houdini in C++, or the light department can have someone writing a new shader in C++. VFX studios are usually not writing their own shaders or renderers. We build on top of existing solutions and glue them together with Python. Let's have a look of what the backend of a VFX company usually is, what allows the work to happen. So as we saw, there are many departments, applications, and data formats being used. Pipeline needs to support all of these different departments and workflows. We handle the standardization of products being passed from one department to the next. We implement libraries, services, and tools to make life easier for everyone. At the core of the pipeline, there are four main concepts that are common in all VFX studios. They are the asset system, the render farm, the disk storage, and managing software packages. Let's start with the asset system. The asset system stores all the data created by artists. Everything an artist produces or used to produce something is an asset. We can have thousands of artists working to the same feature film, and they create, import, and export assets all day long. Artists also iterate in their work, generating multiple asset versions of a given asset. So for example, say Iron Man in a movie, there were hundreds of versions of it before the final one, which actually got approved and put in the screen. We need to track all the metadata on those assets, who created it, who is using it in the pipeline, what was necessary to produce it, if this particular version was approved by the client, where it is on disk, and so on. It's actually possible to see. So in this example, let's follow how an artist might interact with the asset system to do work. So a 3D artist would start working in Maya by importing the Wonder Woman bundle asset to his application. In this case, we can see how the Wonder Woman bundle version 3 is composed of the body and the body geometry version 5 plus the armor geometry version 3. The artist then imports a texture asset and applies it to the Wonder Woman bundle. When the artist is done, she exports new assets for other departments to consume. In this example, the artist is exporting the My Work file, a video, and a rendered image. A layout artist down the pipeline can now import this texture model into his scene. So the artist usually is not calling Python from the libraries. We have all the major VFX applications, we have some Qt bindings, and we can develop our own UIs in Qt. So for the artist, it looks pretty much like a regular UI where you just import stuff, and we have a lot of things happening in the backend. So a key point of an asset system is managing dependencies. Dependencies are key to know which assets are necessary to generate other assets. For example, which files were necessary to generate the final image of Wonder Woman? If we have the final image tracked by the asset system, we can trace back. We can see that for the final image, we used a Maya file version 1, which used a Wonder Woman texture and a bundle and so on. If the shot was final at this point, we could remove every other version of the disk, freeing some space. There's more to dependencies. For example, artists need to be notified if they are working an out-of-date asset. And also, artists should not be able to delete files that are actively being used by other artists. From the client raw image to the final image we produce, there can be thousands of levels of dependencies, all which need to be traversed very frequently through the asset system. So the render farm. The render farm is responsible for rendering. Without getting to more details, rendering is the process of converting generated an image from a 2D or a 3D model. Rendering frames is very CPU and I/O intensive, and is usually parallelized into many high-end computers. It's also worth mentioning that artists cannot work on their machine if it's rendering. So for those reasons, at VFX studios, we always need a render farm. So render farms are used for high-performance computing. They are formed of many computers, or what we call render nodes. Those render nodes are then split into clusters. A cluster of slow computers that can be used for rendering images with a low level of detail, for example. Or we can also have show-based cluster like the VFX PyCon cluster. Render jobs are then submitted by artists and contain tasks that need to be executed, as well as requirements. For example, render an image sequence using 50 gigs of RAM with high priority. The render farm manager deals with scaling those tasks into the available render node. It is like a supercomputer with thousands of cores, terabytes of RAMs, and petabytes of disks. The render farm manager also deals with dependency between jobs, frames, and also manage the render node themselves. So this is a very simple code snippet. It would submit a job to the farm that would echo the frame numbers. The render farm manager is then dispatching each individual frame to a different node, if that node has at least 2 cores and 4 gigs of RAM available. Usually jobs have dependencies. For example, only start a job to encode an image sequence into a QuickTime movie after the image has been rendered as well. The dependency graphs can become very big with lots of jobs doing multiple steps. With lots of jobs doing multiple steps of the pipeline before having the final image. So you can have a chain of dependencies in the jobs, each one using the output of the previous job. Custom Python libraries and services are built for job submission, tracking the render process at real time, getting like memory usage, CPU usage, I/O usage, and for doing actions to active jobs like blocking, unblocking, requeuing, and failing a job. This is an example of farm manager UI that an artist will usually have access to. They can check the progress of their jobs, the frames, they can check the logs of the jobs, they can preview the image in real time while they are being rendered in other machines. And they can also do jobs like requeuing a frame. Recently we worked on the Netflix film Okja. Okja was a 4K job with lots of water and creature work. A single frame in Okja could take up to 125 hours per frame into a single machine. So that machine had to be running for at least 120 hours for the frame to render. Say a shot had 2,000 frames, that would take rendering Okja shot 27 years, and I'm talking about an individual shot. Artists need to iterate on their work, making it necessary to submit jobs to the farm multiple times during the day. To give more numbers, the Vancouver farm had around 1,500 nodes at the time of this show. Each one had 50 cores and 100 gigs of RAM, giving us a sum of 56,000 cores to do work and 150 terabytes of RAM. We use bare metal computers. We don't use virtualization because I/O really counts for us, so we actually have boxes, the old style. All those render nodes need to read assets from the disk and write image to the disk, which brings us to our next subject, the disk. So traditionally, NFS is used by VFX houses. Every machine, artist, or render node has the NFS mounted. Artists are always working on the NFS, making it easy to share work and have it available in the render farm. Disk I/O is a must. Thousands of farm jobs might be at the same time trying to read an asset file and write the render result to the file system. We have 21 nodes in the NFS server setup in Vancouver. Each one has 100 gigs of RAM and 1.6 terabytes in SSD just for caching. Disk space is always a challenge. On any given day, there are hundreds of artists creating assets, and those assets can have terabytes of space in the disk. So while NFS works for one studio, it doesn't work when you're trying to do a global pipeline. When the work is trying to be shared through sites and you try to mount NFS over once, you hit problems like latency or file corruption become more often. So we need a separate service just to deal with scheduling transfers between sites. It's kind of a transfer service, very similar to the render farm where you submit jobs like, hey, transfer this file path to that studio. You have priorities and they happen asynchronously. So in summary, we have a good number of Python libraries and services dealing with disk management. They crawl the file system, they store metadata about the crawls, they deal with transfer between sites, they talk with the asset system and wrap third-party software and so on. So because of all the effort that goes into NFS, NFS is also leveraged for software packages. When releasing a new version of a software package, we simply install its location on the NFS. Then every machine in the studio will have access to that software package. So all the machines in the studio, again, they need to be able to execute any kind of work. Usually when an artist logs off at 6 o'clock, his machine gets absorbed by the render farm and can do some renders overnight. Having everyone sharing the same file system makes this task much easier. However, different shows in the same studio might be using completely different versions of software. Even within a show, we can have different tasks, say model and lighting, using different versions of Maya and the pipeline libraries. We solved this issue by having just-in-time resolving of the runtime environment that's necessary to do work. And we don't install anything in the system level. Everything is installed in the NFS, just to be very clear. For that, we use Res. Res is an open source Python tool that allows for resolving a list of packages and their dependencies into an environment. So as an artist, I start my working by saying, hey, I'm on shot ABC 1000 from VFX PyCon, and then I type like Maya. What I get back is an environment running Maya, but it also has all the Python libraries loaded in. Someone in a different shot might have a different version of Maya and pipeline libraries. So the package definition file in Res takes care of manipulating environment variables like the Python path, LED library path, and so on. It also can execute pre and post installation scripts, like after doing what we call a Res release, it calls the transfer service to do a transfer of the package to all the locations around the world that we have. So in this example, we can see like you res env into a environment that would have requests, Python, PyMongo, and those would be separate res packages, which have some metadata like where the Python modules are and the version of the package and what package they require. And what you get back is an environment with PyMongo, Python, and requests. And here is a very simple one for Houdini. Usually, and that's a little bit tricky, when we have a problem, sometimes you can't even render the image because like we have over 500 libraries and tools in the studio. So this can be very problematic. Runtime dependencies start to become very tricky, like with JavaScript in the dependency how, only it's Python. For example, an innocent change in the order of your function arguments can make your library backwards incompatible, and you might not release as a major version because you don't see it as a big deal. But now every other library or tool that was using your library, if it was locked only to major versions and automatically update the bug fix version, would break. Other issues is like exposing credentials to the libraries. So like if at runtime your library is connecting to a database, that means that every artist machine has the credentials to the database. It also makes updating the database schema very difficult because you can have shows locked to different library versions. So you might have a show in a very old library version accessing the database directly. And shows usually do lock when they're close to delivering trailers or movies, so they don't even get updates. Abstracting some of the core functionality of the pipeline services gave us much more stability and freedom to iterate in the backend. It decouples the backend of the pipeline from the VFX tools and libraries. So what we saw so far are the building blocks necessary to build the backend. We have the asset service, the farm service, the disk service. By offering those services over the network, they are not coupled to the runtime dependencies. Our stack in the service is very common. We have Unicorn behind Nginx, using green threads and serving the requests. Services usually also have some RabbitMQ workers consuming MQP messages for tasks that need to be asynchronous, for instance, generating a thumbnail for an image. There are some challenges with going to the service route though. Downtime is really not an option. If anyone works on VFX, they know how hard the deadlines are. And having downtime in the asset system after 5 days of rendering a frame in the farm means you need now other 5 days, and no one's going to change the movie release date for you. So another challenge as well working in VFX, because of network compliancy, our internet access is extremely limited. Most of our data cannot touch the internet. So we have our own network cables. We are isolated from Google Cloud, Amazon, AWS, and so on, meaning we have to keep everything on premises. But not only that, we cannot pip install something easily or git clone a cool project to try it out. It does add some slowness to the whole process. So we have to, when designing our own services, take everything into account, like power outrage, disk failures, and network connectivity issues. High availability is a must. I used to work in like a cloud-based startup before, and like when doing my service using Heroku or AWS, you usually don't think about disks failing or power outrage, but it happens. So to deal with the challenge, we came up with an architecture that has been working really well for us. Every VM is provisioned with Zabbix, Logstash, and Consul. It's the base level that a service needs, which means we can see the metrics in real time. We can see centralized logs in Kibana for every service. And we use Consul for service discovery and load balancing. Globally, it looks like that, where we have Consul running different data centers. We have the whole services mirrored in each location. That allows the studio to work completely offline in case of network partitions, but it also gives us some challenges. So in sharing work between sites, not everything can be an island, obviously, if you're sharing work. So we heavily rely on RabbitMQ federation to do cross-site work. MQP messages can be sent globally, and then each site can act on it. And if the connection between sites is interrupted, RabbitMQ just queue the message and send them over when the network partition is solved. For example, an asset being approved in Vancouver, we will emit an event like asset approved with the metadata about the asset. And then each location will receive this event and can do stuff about it, like notifying an artist or simply updating a local database. Some services have a simpler approach because they can afford to, where you have a master database in one location and every other location will have a read replica. So in case of network failures, everyone becomes read-only, basically. And finally, we're also investigating CouchDB and master-to-master replication. Seems like CouchDB does really well, deals really well with network partitions and merging the documents when the network is back up. It's still not in production, though. So we've seen how we architect our servers at Metal Studios. Just as important is how we make them stay up. We rely on Ansible for configuration management. Ansible lets you abstract a set of tasks into a playbook or a row, and they run idempotently, so you can run them as many times as you want, and the service will be in the same final state. Every service goes through a deployment pipeline. We first run code in a dev VM. Unit tests are run there. We have Jenkins CI to make sure nothing is broken. Then we have a staging environment, so we basically redeploy to staging. Then we have integration tests and load tests running on the staging VMs. And finally, when everything is good, we release to the production environment. The only difference between the environments are environment variables. You have the same artifact, like a REST package, being deployed to the different ones, and they just source the config from environment variables, which are different. As I said, we have common roles in Ansible for systems metrics, centralized logging, and service discovery. This is what it looks like for, say, the farm service. We have different VMs in different locations and modes, like dev, stage mode, production, LA, Vancouver, and New York. And we simply rerun the playbook against the different locations dash modes. You can see how we have common roles there, like Zabbix agent, Consul agent, the syslog stuff for centralized logging, and then we can install Nginx as well in this case. And farm service is the only like custom role that we wrote for this service. Everything else taken care of when you're deploying a new service. So Consul is like a Swiss army knife. It has multiple components, but as whole, it's a tool for discovering and configuring services in the infrastructure. It deals with health check, DNS, for instance. You can make a request for a specific site, which won't fail over to another location if the service is down in that site, or a global request, which will happily geographically fail over to other data centers in case your service is down in the data center. It also has a key value store that we leverage for some of the configuration. It has an ACL very similar to the Amazon ACL. It has been basically, we just installed and it runs. And I have to run over the slides because I'm going out of time. So here we can have an example of the JSON file and the Consul UI. We can see all the servers in our data centers here. We use Elk for centralized logging and metrics. This is an example of a dashboard that would have all the system metrics for a service there. So you can see how it's load balancing between two VMs in the pie chart, the average HTTP latency or the percentiles, and etc. We use Zabbix for more like VM metrics, like CPU, memory, and disk. It's collected periodically, sent to a server which has alerts, and we display it on Grafana. So we have two kinds of views. One is very generic, like is the VM up or not? And the other one would be a more specific one, like in this case for Redis. So what do we want? We want to empower the artists so they they don't have to worry about anything I just said. They should just care about their art and craft. We want to empower the studios to do better predictions. And we want to, and automation is a key part of all of that. Our images are property of the respective owners, just doing my diligence. And I want to give a special thanks to Mitchell, who works with me at Method. He has helped me to do all of the cool images, because mine would be a boring black and white presentation. Thank you.